All right. So we're going to pick up with the other half. Part 2, I call it, number 36. There you go. So the force between two bodies having identical electric charges. This is purely electrostatics. In other words, if you have two identical charges, what kind of a force are you going to have? Right? Repulsive, even if they're both negative, it's going to be repulsive. All right, so which one is that? Oh, A, a force of repulsion. Right? If the charges are negative and one of attraction, if they're positive, I don't think so. Increases as the bodies move apart. No, actually decreases as they get further apart. Independent of distance? No. Directly proportional to the distance between them. Actually, it's inversely proportional to the square of the distance between them. If you're measuring the force between two charged particles is proportional to the inverse of the square of the distance, otherwise known as the inverse square law. That works for these repulsions. It works for radiation. Right? If let's see, how far away is Mars? 150 million. We're 90 million. Right? So it's not quite twice as far. But if it were twice as far, it'd only get 1/4 of the radiation. That's probably more information than you wanted. The answer is A. I'm sure that's the punchline is what you really want. Oh yeah. Are you going to take it in person or online?
When is it?
Well, everybody in here says Tuesday's fine with them at the regular time. And that usually works out for most of my students in every semester. I don't know why the school comes up with these final exam schedules. You know, what purpose does that serve? You've already got the schedule with your students showing up at a certain time. They've got work schedules, they've got kids,
Right.
you know, things like that. It's just, who knows?
You said the final lab notebook check is Tuesday as well, right?
Yeah, well, I guess that would depend on whether you're here or not.
Right.
The only other option you have is to photograph all the pages you filled in
If you don't come,
and submit them in Brightspace.
if you come Tuesday.
Yeah. If you're going to take it online, the school says you have to have them in by Wednesday midnight.
It does.
That's fine. Yeah. Sooner the better, actually.
Yeah.
It's less stress on me trying to get my grades in.
Right.
And you know sooner too. Because I've set the Brightspace to close, I think, midnight on Sunday.
Yeah.
Just for late assignments and things. I can do that here. At Southern, they won't let you do it. It's going to close on Friday evening. That's it. They don't give us the option. So we're a little more flexible here.
And that's next Friday?
When
Friday
Yes.
is?
Yes, a week from Friday. Don't confuse me like that.
Yeah, sorry. Starting to scare me there.
Yeah, I came in this morning. I was going to teach the class at 9 o'clock. Wrong class. That's my 100 class.
Yeah, I say, because I come here on Tuesdays
Uh-huh.
and Thursdays. Yeah, and I see you here. Are you
Yeah.
teaching just a Zoom?
All by myself. Yeah.
Yeah.
It's a modality that's not official yet. I've been piloting it for several semesters. Call it HighFlex. You can take it Zoom, you can take it in person, you can take it purely web.
I like this whole hybrid thing.
Yeah.
Zoom sometimes. And
Yeah.
come in. Really, I was like, I get kids and everything else.
Yeah, the only thing I can't well, I could, but I don't like to, is online labs,
Yeah.
because they're just not the same.
I went to Bridge Valley last semester and they had an online lab with A&P class and it really a joke.
Yeah, I mean, this The whole purpose of a lab is get your hands dirty. But it's something that I developed during COVID. You know, those GoPro camera shots have you seen those?
Yeah, no, that's a good idea.
I could improve on it. That was sort of a last minute thing, but it worked for its purposes. And you can still watch the videos ahead of time if you want to see how the lab's going to proceed. And then when you come in, you're not completely lost.
I didn't know. Do you know that a paper copy of this? My computer was not good.
This one?
Oh, I'm sorry, I didn't know something.
That's all right.
Thank you.
I try to keep extras. Okay, where were we? 37? All right. 37. I don't have to rush either. I mean, I can stay as long as you need me. I've already picked up my vehicle. It's been repaired. I got popped in the parking lot by another student.
Here?
Yeah.
Dang.
Yeah. It was nobody's fault. We just didn't see each other.
What kind of damage did it do?
Superficial,
Cosmetic.
which means still lots of money. But my insurance came through. Yeah, I paid for it today. It was like $1,500.
Getting a $1,500.
And it just pushed in the bumper and cracked the tail light.
Those lights are expensive.
They probably had to replace the whole back end. Okay, let's get back to chemistry. Which of the following molecules has no dipole moment? All right. A, B, C, D, and E. And so we got carbon dioxide, ammonia, water, all or none. We're looking for the one with no dipole. Okay. What two things do you need to know in order to determine whether a molecule has a dipole moment, whether it's polar or nonpolar? The bonds have to be polar first, right? What's after that? Starts with a G. Geometry.
Yeah.
You got to know the shape of the molecule, right? How are those polar bonds oriented? I mean, are they in such a way that they cancel each other out? Or are they offset some way so that their vector addition gives you a dipole moment? And we've drawn all these before, right? Water looks like this. But if you're confronted with a molecule that we've not done before, you have to draw the Lewis dot structure first, if you remember how to do that. Ammonia is like this. It's got hydrogen in the back, and then it's got hydrogen over here and here and here, and this triangular base, and then it's got a lone pair right up there. And then let me see if I can draw this one right. One carbon and two oxygens. Let's see, and you got like that. So everybody's got an octet, and this is the shape of that molecule, the shape of this one, and the shape of that one. Right, so this bond is polar. These two bonds are polar. That means overall, it's polar. These bonds are polar. That plus that lone pair is this one. Like that. These bonds are polar, but they're 180 degrees from each other, so they cancel each other out. This one has no dipole moment. Okay. 38. Let's see, let me get it up here so we can see it better. Choose the molecule with the strongest bond. Okay, so it gets difluoride, difluorine, dichlorine, dibromine, excuse me, iodine. I put this one in there. Let's see, all equal. Let's see, this is E. Can I spell backwards? C. D. A. The trend would be the strength of the bond increases as you go up in a group. First of all, the electronegativities increase as you go this way. So that's one factor. The other factor is how much overlap do you get in your bonds? Because that strengthens the bond if you can get more overlap of your orbitals. Since these are big, you have less overlap, and you have lots of core electrons and lots of protons here, and it pushes the centers way far away, and then they get closer here, and they get closer here, they get really close here. Okay, that's the key. They get stronger, 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 but when you get this close together, you're starting to feel the repulsive forces of both electrons and protons. So when these two fluorines get really close together, then their, let's see, 9 protons start to weaken the bond. So the strongest one, counterintuitively, is fluorine. It has the strongest bond of that family. Okay. And that's how you do it if you don't have the actual values. If you have the values, then it's a no-brainer. You just compare the numbers. 39. In the gaseous phase, which of the following diatomic molecules would be most polar? Okay, so we got cesium fluoride, cesium chloride, sodium fluoride, and lithium fluoride. All right, in this case, they're all ionic. Right? You got metal on metal, metal on metal, all the way. And cesiums and sodiums and lithiums are way over on the far left, and these are way over on the far right. So we know they're all ionic. So we need to approach this not from the covalent standpoint, but from the ionic electrostatic standpoint. And two things that influence the strength of an electrostatic bond, an ionic bond. One is the size of the charges, and the other is how close are they. Okay, those are the two factors that influence electrostatic attractions. Right, so this one is, yeah, this one's always this +1, +1, +1 cesium. They're all +1, okay, and all -1s. Okay, so that removes the size of the charge factor. Now we say which ones are closer. Well, let's see. And when you think of the ions, how big are they? Right. These are the biggest ones. Chlorine's big, cesium's really big, so this is going to be the weakest. All right. This will be a little stronger because that fluorine can get closer. It's a smaller molecule, a smaller atom, smaller ion. Sodium is smaller than cesium, though, right? So that's going to let this one out. Lithium is really small. It's smaller than sodium. So I think that will be the strongest bond. Right? They've all got the same charge differences, but lithium and fluorine are the smallest of their respective ions. Fluorine is smaller than chlorine. Lithium is smallest of all of these. So that gets them really close, and that bond should be the strongest of all. All right. Number 40. This one ought to look familiar. Right, there's benzene. The first one is benzene. Second one, we're still in a cyclic compound, only this one is drawn one. Here we go. This one has one there and one there, is it? Yeah, It doesn't matter, just rotate it a little bit and you get two. And then we have this one. We just want double bond. Now what's the question? Which molecules have equivalent carbon-carbon bonds throughout the molecule? Double bonds typically are shorter than single bonds. And that's true for any straight compounds. If we could straighten this one out and that one out, then the double bonds would have the carbon atoms. Remember, these are carbons right here. All those carbons. They're closer together with a double bond than they are with a single. So this one would be closer than any of these others. And what that does is add strain to the molecule. Because if this bond is shorter, these others have to compensate for that strain. This one is strained on those two. These are short, short. These are long, long, long. The thing about this one is these alternating single and double bonds allow the p orbitals to overlap in sort of a torus. And it forms, actually, benzene is often written this way to show that lost the right term. The electron density is distributed over the entire ring, and that stabilizes it. So every bond in this molecule is, and has been confirmed by experiment, is the same length. Every bond is the same length. So we really don't have any double singles in that molecule. This one would have a diffuse nature like that. This one would only be those two. So these three bonds are probably the same length. But all 6 of those bonds are exactly the same length. They're equivalent bonds, in other words. And that's number 1. Right. A. Okay.
Can we go back to 39 for a second?
Mm-hmm.
You said it was lithium chloride.
Oh, wait a minute. What was I looking at?
Back in our study guide for that chapter, you said it was A.
Which of the following diatomic molecules would be the most polar?
Said they were the atoms for the
Oh, I was answering the wrong question. Yeah, that's the problem. Lithium fluoride would have the strongest bond, but the most polar would be the two that were the most electronegative difference between the two. Okay, so 39 would be. Fluorine and cesium are the furthest apart. So it would be A. Yeah, you're right. That would be the most polar bond of all. You have to stop me when I do that. Right? I mean, unless I'm just feel like you're being snowed. No, I was just off on the wrong track. That 39 is A. Where did I get? Oh, I was looking at this one up here. Strongest bond, and I was applying it to this one. Yeah. Far too often. 41. Question is, did you get anything out of it? I mean, was my big mistake worth it? The electron configuration of a particular diatomic species. Okay. You'll notice that with those stars in there, we're talking about molecular orbitals, right? Because those are the anti-bonding. What is the bond order for this species? Oh, okay. So I don't have to draw it up there. We'll just say, what is bond order? Right? It's the number of electrons for bonding minus number of electrons for anti-bonding divided by 2. So the bonding electrons would be 2, 4, plus 4 is 8. Is 8. Minus antibonding, 2 and 2, that's 4. Divided by 2. So 8 minus 4 is 4, divided by 2 is 2. Okay, so D's the answer to that. All right, 42. Let's see, consider this molecule, specify the hybridization of each carbon atom in the following order. Okay, so those 1 through 5 is just, they're just numbering the carbons. They're not subscripts of any kind. How many we got? 5 carbons? 1, 2, 3, 4, 5. And this one has 2 hydrogens. All right, let's do it this way. Double bond here, 2 hydrogens there. I'm expanding it from the shorthand to something resembling a structure. There we go. Then this carbon has an oxygen on it. And it has 2 hydrogens here. And this one has nitrogen. Okay, so this one's 1, 2, 3, 4, 5. All right, if we're gonna determine the hybridization, we need to see if there are any lone pairs here also. The nice thing about carbon, it's usually fairly well behaved, unless you get a graduate student assigned a project where he needs to force them to do strange things. Most of the time, they're well behaved. 2, 4, 6, 8. So that one's got an octet. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. And 2, 4, 6, 8. Now, how about this oxygen? 2, 4, 6, 8. That oxygen has 2 lone pairs. Okay. And this 2, 4, 6, 8. That nitrogen has a lone pair. So now we can, well, actually, it doesn't matter for the nitrogen because we're only interested in the carbons anyway. So this has 3 groups in it, right? sp2. This one has 1, 2, 3, sp2. 1, 2, 3, sp2. 1, 2, 3, 4, sp3. 1, 2, sp. Okay. So which one is that?
A.
2, 2, 2, 3, and 1. 2, 2, 2, 3. Yeah, A. Actually, we didn't need the lone pairs because there were no questions about the oxygen or the nitrogen. All right. Get this out of my way. There we go. 43. Which of the following statements describes the Heisenberg uncertainty principle? I should have looked this up before I came to class. I don't want to try to write it up there. What Heisenberg said was, for very small particles, like subatomic particles in particular, you can't know both where the thing is, which is delta x, that is change in position. You can't know where it is, and the momentum, that's our momentum, which would be mass times velocity. You can't know its momentum, and since the mass, if you're talking about one particle, one type of particle, the mass is going to be constant. So you're really talking about how fast it's going. So you can't define how fast it's going and where it is at the same time. And this refers to energy also. Okay, so which one approaches that Impossible to accurately know both the exact location and the momentum. That's it. Hey. Location and momentum. You can know one. If you fix one, you can't know with any accuracy what its momentum is. Or if you know what its momentum or its energy is, you can't know where it's located. That's why when we talk about orbitals around an atom, we're saying that we're fixing the energy. Right? If an electron is in that orbital, it has a certain amount of certain energy. Right? So we're saying the energy part we want to know very accurately. In that case, then you have to just draw your orbitals as kind of diffuse regions where you might find the electron. And that seems to be more useful than actually knowing where the electron is. Right. 44, Mendeleev. It's a good thing Mendeleev came along when he did. Waited a few more years for the Russian Revolution and nothing like this would have come out of Russia. It's not so much the smarts of your people, it's the system they have to work in. Because we've got a lot of, America's just chock full of foreigners that make Nobel Prizes this way and that way. Right? And all free countries like that tend to produce economically, scientifically, and so forth. That's what I get down off my soapbox now. Mendeleev is given the most credit for the concept of the periodic table of elements because let's see. He emphasized its usefulness in predicting the existence of properties of unknown elements. That's exactly right. See.
We should see it, I guess.
Yeah.
I just remembered it. He played it. It was so on thunder that day.
There were other people who were working on one other person that was working on periodic table, but they just kind of dropped it. And Mendeleev says, wait a minute, there's supposed to be an element here, right? The one that should go here, that I would put here, needs to go over here. It says there's an element there. It's going to have these properties. It's going to have this weight, right? Sure enough, they found it, and that sealed it for him. He gets the credit, and rightfully so. He also gave credit to his inspiration, right? Cannizzaro. Remember, he was the one with handing out his papers at the Karlsruhe University. He gave, in his publications, he gave Cannizzaro and his mentor, Avogadro, credit for solving the problem of how you assign weights to these elements. Because up to that point, that was just a mess. Anyway, 45. Nitrogen has 5 valence electrons. Which of the following electronic configuration represents the ground state for N minus? Right. So it's going to have 7, but 2 of those are 1s's. Right. And the 2s2 and 2p3 means 3, 4, 5, 6, 7, but it's got an extra one. Right. And remember, p orbitals have 3 sublevels. So we'd start off like this, but we're going to add one more. So where does it go? Right there. Hund's rule. Once we get all 3 of these sublevels filled with 1 spin, then you can pair them up opposite spin. And that's where that ion, that extra electron goes. So it should be, let's see, they don't include 1s. So 2s2 would either be A, D, or E. And then actually A would be the neutral atom, and E would have the opposite spins here, and then these 2 lungs. So E should be the best answer for I thought you were gonna beat me to it. All right. That was 45. Let's see. Yep, we can get those in there. If I can just bring this down so I can see what this stuff is doing. 46. An element has the electronic configuration. All right, we're using our abbreviated version. Argon has 18. And then we're kicking off from argon. Argon is in the third period. So we're going to pick up with 4s. Yes, 4s2. And then we're going to go to 3d, cross over the transitions. And therefore, and then we're going back to 4p2. So where would that be located? Like 4p2, right here. It depends on your choices. This is germanium. 32. So what would it be? Not a transition. It's before you cross the line, so it'd be a metal. Actually, a metalloid. Right? It's right on the line. Spell it right. Metalloid, because of where it's located. Now, if you don't have metalloid as a choice, metal's your best answer. All right. Oh, 47 is already up there. In which group do all the elements have the same number of valence electrons? So what are we looking for here? They're all in the same group, all in the same family. Okay. How about A has argon in it? That's the only noble gas in that group. So that's not it. Sodium, calcium, barium. Let's see. Sodium. No. Sodium and calcium are in different neighborhoods. How about C? Phosphorus, sulfur, and chlorine. Now they're in the same period, not the same group. It's not looking good for the home team. Phosphorus, arsenic. Yep. Phosphorus, arsenic. Oh, selenium's off to in the chalcogens. All right. So that's not it either. So I guess none of them are right. All right. Oops. Pick up 48. Which of the following was not an elemental property usually predicted by Mendeleev or undiscovered elements? Electron configuration. Did Mendeleev know anything about electron configuration? No. That was before, that was after his time. Right, so definitely A is not one. Oh, and we don't have any odd ones, like two of the above or none of the above. All right, we found our answer. Electronic configuration is something that he knew nothing about. Let's see here. Can I get all of them? Yeah, I can get all those. Get 49 and 50 together. Which of the following statements is always true concerning a reaction represented by, there's a typo there, isn't it? It should be a Y, not a 49. Represented by the following balanced equation. Which of the following statements is always true? We got, oops, C2H6. Better put the phases in there because the question may refer to phases also. 6 waters, liquid, and this gas, and carbon dioxide. And we're told that it's balanced. If we have equal masses of C2H6 and O2, there's no limiting reactant. Limiting. All right. Equal masses. So if we have X grams of this one and X grams of that one, how many moles do you have? Well, let's make it simple. Let's say we have 100 grams. 100 grams of each one. How many moles do we have of this one? Right. How many grams per mole? Well, 2 carbons, right? Well, 0.01. 6 hydrogens, 1.01. Which would be, time for my calculator. That's it, 6.06 for the hydrogens and 2402 for the carbons. That's 3008. Right. So divide that into 100, and we get 3.32 moles. 100 grams of oxygen. Right. What's the magic number here? We do that one in your head. 2 times 16. So 32 into 100. 3.125. 3.13 moles. Okay, so this is, if we have equal masses, right, we have pretty close to equal moles, but the ratio is 7:2. You need, for every 2 of these, you need 7 of those. Right? So which one's going to run out? That one. Right? There's not enough. 2 times this would be 6. 7 times that would be 21. So this one, under the first scenario, this one is limiting. If we have equal masses, there's no limiting. All right, so A is false. How about B? If we have an equal number of moles, there's no limiting. Well, they're pretty close to equal now. Right? So B's another way of saying A is wrong. How about C? What does C say? If we have more mass of C2H6 than O2, that if we have more mass of C2H6, then O2 must be limiting. Well, yeah, it's going to be limiting anyway. So, I mean, that's true. If we have more mass of O2, then C2H6 must be limited. Well, if you have, it doesn't say how much more. If you have, I think what they're saying is if you have more mass of this than you do of that, then this will be limiting. Or if you have more mass of this than you do of that, then this would be limiting. And there'd have to be a whole lot more mass of them. The best answer is C. Right? D could be if we were given more information, but we're not. So we have to eliminate D and go for the best answer. None of these statements is true. That's wrong. C is true. Right? And D could be true if we knew how much. Right? But it doesn't tell us enough to go for D. 50. What's 50 about? Oh, acids and bases. Okay. Well, let's see. Is sulfuric acid a strong acid? Yep. HNO3, nitric acid. That's a strong acid, right? So B's wrong. Barium hydroxide. Barium. Yeah. Alkaline earth hydroxides are all strong bases. HCl, hydrochloric acid is strong. NH3, ammonia. Is that a weak base? Yeah, that's a weak base. So B is the only one that's mislabeled. Right. Could you do that one? say I switched it around and say, okay, nitric is a strong acid. And then I say, ammonia is a strong base. Right? That one would be incorrect. Right? Just giving you a heads up. In case I get sneaky. Let's see. 51 through 53. Aqueous solution of barium chloride and silver nitrate are mixed to form silver chloride and barium nitrate. Oh, they even tell you that the silver chloride's solid. They tell you what the precipitate is, so that's nice. A molecular equation, ionic equation, and net. Okay, so we'll put this one together and then answer all three questions. So we need to know how to write barium chloride. Right. Chlorine is a -1. Barium is an alkaline earth, so it's +2. It means we need 2 of those in aqueous solution. And then silver nitrate is the next one. Yeah. Silver is a +1 charge. Nitrate is polyatomic with a -1 charge. And all nitrates are soluble, so that one's still in solution until we put them together, of course. And then we get silver chloride is our precipitate. And what's left? Barium nitrate. And we need 2 of these. Now, barium's a 2+, nitrate's a -1. And this is aqueous solution. All right, so we need to balance this one first. Most of these double replacement reactions with a precipitation are fairly easy to balance. I mean, you don't even have to set up a budget. So 1 barium, see, 2 nitrates. Let's start there. 2 nitrates. Now we need 2 silvers. That gives us 2 chlorines. There we go. Now we're balanced. That's the complete molecular equation. And let's see, which one of these is present? Not the first one. Second one. B is there. C is not there. D is not there. 3 silver. Okay, B is the best answer. This one. So this one is 51. Okay. Now how do we write the complete ionic equation? All right. If it says aqueous, this is a soluble salt. These ions are separate in solution. They're just floating around. Right. We write it this way for convenience. All right, so we got 1 barium with what charge? 2+, and it's aqueous. We got 2 chlorides, and they're both aqueous. Right. Now we have 2 silvers. They're aqueous, and 2 nitrates. And they're aqueous. We have to write this one as is. Okay, because it's a solid. And then we have a barium over here with the 2+. And 2 nitrates that are also aqueous. We can't simplify it any further, right? Because we have 1s and 2s. Can't divide it by something and simplify it. So now let's look at 52 and see which one of those is up here. 2 bariums? Nope. 1 chloride? Nope. 2 silvers? Yep, there it is. So that's 52. Right? I don't think the rest of them are good. Right. The rest of them are wrong. That's the right one for 52. Now, how do we do the net ionic equation? We cancel terms from both sides, right? The spectators. Barium's a spectator on both sides. Cancel it out. How about nitrate? Yep, there are 2 nitrates here, 2 nitrates there. So what do we have left? We have silver, 2 silvers, 2 chlorides, and 2 silver chlorides. Now this one can be reduced because there's a 2, 2, and a 2. So the net ionic equation would then be silver by itself one silver, one chloride, and one silver chloride. Okay, oh, I need to scroll that one, don't I? All right. So, no, only one silver. We don't have barium there, we don't have nitrate. We put that hydrogen there. It wasn't even in the original equation. Silver chloride solid. Oh, wait a minute. There's really, all right. If you're confronted with this issue, the best answer would be this one before we reduced it. That's two silvers, yeah. Two silvers. Because the rest of them don't make any sense. Silver chloride is not aqueous. All right. Let's see how we're doing. 54. We got some formatting problems there. You're holding two balloons, orange balloon and a blue balloon. The orange balloon is filled with neon, the blue balloon is filled with argon. The orange balloon is twice the volume of the blue. So the orange one is here, filled with neon. And the argon is here. And the volume of the neon is equal to twice the volume of the argon, which represents the mass ratio of neon and argon. All right, what's the mass of neon? We're going to estimate, say it's about 20, and argon is about 40. Okay. So how do we approach this? Well, Avogadro said that if this volume is half of that volume and all the other factors are the same, if temperature is the same and pressure is the same, pressure would have to be the same if they're in balloons. What happens to the moles? Well, if the volumes are the same, the moles are equal, but this volume is half of that. So this one has the moles of neon equals twice the moles of argon. Okay. So how do we tell mass from moles? Remember, molar mass is mass per mole. All right, so if the value here is 40, let's see, number of moles, here we go, equals some value, molar mass. Make it a big M like that. That's molar mass. If the molar mass is 40 versus 20, then we solve for N equals molar mass times mass. How do we, well, actually we should solve for mass, shouldn't we? Because that's the answer. We're comparing the masses. The mass is equal to molar mass times the number of moles. All right. So if the molar mass here is twice as big for argon, right, this is 2 times, but the number of moles would be half. Right? So that means these cancel each other out and the masses should be equal. They should be exactly equal. 1 to 1. That makes it 8, right? I think the review document for this chapter has a bunch of algebra, half a page of algebra. This seems to work quicker. Let's see, 55. Oh, calorimeter problem. Okay. Let's see, what's the question? Which metal was used? All right. We're going to identify the metal based upon its specific heat. And here the specific heat variable is a C. And I think our textbook and our labs, we used a small s, but they mean the same thing. So 45 gram sample of a metal, mass is equal to 45.9 grams. Yeah. And the sample is heated to 95.2 degrees. So temperature, initial temperature of the metal is 95.2 degrees C. Okay. Place it in a calorimeter with 120 grams of water. So this is the mass of the metal. This is the temperature of the metal. It's the mass of the water equals 120 grams. Okay. And it's initially at 21.6, was it? Yeah, degrees C. Okay. The final temperature is going to be the same for both of them, because you put that metal in the calorimeter with the water, and when they come to equilibrium, the final temperature is going to be both the same for both of them, which is 24.5. There we go. Okay, now we got all our data up here. Well, except for the S of water. 4.18, right? Joules per gram degree C. Okay. Now, what formula are we going to use? Remember, this calorimeter is an isolated system. Heat and matter don't cross the boundaries. So everything that happens in Vegas stays in Vegas. That means everything that happens in that calorimeter has to be equal to 0. One other thing they didn't tell us was what's the contribution of the calorimeter. We have to assume it's 0. The calorimeter doesn't contribute anything, doesn't absorb heat, doesn't give off heat. So we only have to be concerned with the heat change of the metal plus the heat change of water. So the heat change of the metal is going to be what? Well, the mass times the specific heat times its change in temperature. Right? And that's the same thing for water. Mass of water times its specific heat times its change in temperature. Right? And these are two different values. The masses are different, obviously, but this is the specific heat for the metal, and this is the specific heat for the water. Let me see. Let me start way over here. So what's the mass of the metal? 45.9 grams. And we're going to multiply that times specific heat of the metal. We don't know that. That's what we're going to use to find out which metal it is. And what's the change in temperature? It's always final minus initial. So the final temperature of the metal is 24.5 minus initial 95.2 degrees C. Okay. Then we're going to add to that what the water does. And the water's mass is 120.0 grams. And its specific heat, we do know. Joules per gram degree C. All right. And then its change in temperature. This thing's starting to give out on me. Its change in temperature is final minus initial. The final is the same as for the metal. 24.5 minus 21.6 degrees C. There we go. So now we just need to resolve this. That's all the thinking part. The rest is number crunching. So we've got this one, let's see that difference, 24.5, and then subtract 95.2, which is minus 70.7. Okay, and that will be times 45.9. So that's overall minus 3, 2, 4, 5 times specific heat of the metal. Okay. Now what's this term? Well, 24.5 minus 21.6, and that's 2.9 degrees times 4.18, and then times 120. So this one is plus 1455. Right, and that's heat term, so it's going to be joules. All right, so we need to, how are we going to do this? Well, we could put this one over here and make it a negative, and then when you divide this one into it, the negatives cancel. That works. So let's take this one up here, and we're going to say negative 1455 equals negative 3245. And then this one is equal to 1455 divided by 32.5. Let's see. Yeah, they're still in here. So let me flip them and then divide. So I get 0.45 joules per gram degree C. So which one is that? B, iron. Right, B, iron. Okay. All right, 56. Aha. $56. For which of the following transitions does light emitted have the longest wavelength? Longest wavelength. Which means what? The longest wavelength is the smallest frequency. Right? Smallest frequency. So that means, using Planck's equation, which one has, if this is the smallest, it also has the smallest energy. How do you get the smallest energy from an electron transfer? The jump is the smallest you can get between orbitals. Right, so which one of these is the smallest? Well, 4 to 1 is a pretty big jump. 3 to 2 is a little smaller. If we draw our atom like this, right, you have 1 here, and then you have 2 way out here. And then you have 3 a little closer, and then 4 gets even closer. Okay. So we ruled out 4 to 1, that's too big a jump. Okay. A. How about B? 3 to 2. 3 to 2, that's a pretty small jump. So maybe 3 to 2. 3 to 2. 2 to 1. 2 to 1 is too big a jump. It's even a bigger jump than 3 to 2. 4 to 3. There we go. D. 4 to 3. That lets this one out. And 4 to 2. That's a bigger jump. Right? So D should be the best answer. It should be the lowest energy, smallest frequency, longest wavelength. All right, let's see. Oh, 57. Which of the following is an incorrect designation for an atomic orbital? A, B, C, D, E. So what are our choices? 1s, 6s, 3d, 1p, and 4f. Okay. So this is the n number right here. This is the L number here, right? And this is a 0, 0, SPD 3, 2, and 4, as far as the L numbers go. Okay. All right, so which is permitted? Well, for one, you can only have a 0, right? L can only be, it starts with 0 and works its way up to n minus 1, right? So this is the only one it could be, and that one's okay. How about this one? Well, n equals 6, they can have s's also, right? They can all have s's, right? So that was good. How about this one? 3. So what are the possibilities for L with 3? Well, 2, 1, and 0. Right? No, that's not right. SPD, that's right. You know, there's more than one incorrect answer here, isn't there? No, 3D is right. Right, this is 3D right here. Oh, what am I thinking? I'm thinking M spell. Right. For this one, you can go for N. For 1, you can go 0, start at 0. 2, you can start at 0 and go to 1. 3, you start at 0, 1, 2. 4, 0, 1. That's a 2. That's a 1. That's a 3. That's my mistake. 0, 1, and 2. So this one's okay. This one, right? 1 can only have a 0. Right? So that's our bad boy right there. All right, in the molecule XEF2. Oops. XEF2. Yeah, 2. How many pairs of electrons surround xenon? And what's the molecular geometry? So we need to use the localized electron model in PSEPR to find this one. So we have 8 valence electrons here. You have 2 times 7. So that's 14 plus that is equal to 22, right? 22 electrons. Okay, so let's put our xenon here. And let's give it a fluorine on each side. That's 2, 4 minus 4 equals 18. 2, 4, 6, 8, 10, 12. Minus 12 equals 6 electrons. So we have 2, 4, 6. So how many pairs of electrons are there? There are 3 pairs, right? No, wait a minute. How many pairs of electrons? Oh, how many pairs of electrons? 1, 2, 3, 4, 5. I didn't count the bonds. It didn't say lone pairs. It says how many pairs. So 5. There's 5 pairs of electrons. What's the geometry? 1, 2, 3, 4, 5. So if you have 5 groups, what's the electronic geometry? Is that what it's asking for? It's asking for molecular. First, you have to do electronic geometry. And that is trigonal bipyramid. Okay. So if you have a trigonal bipyramid, that is, you have a triangle here, and then up there, down there. So where do the lone pairs go? Lone pairs go on the triangle. They go back here, 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 and the fluorines will be out here, right, with the xenon in the middle. So the molecular geometry is linear. So 5 and linear, C. Right, 58, 59. Okay, we're given some equations, and we're supposed to use Hess's law to find the change in enthalpy for this equation. I've got it worked out down here. I don't know why, just because the rest of them aren't. So let's see, our target equation is for number 59. Our target equation, oh, I might as well get a fresh one. Is calcium carbide. And when you're doing this type of work, Hess's equation, it's good to have the phase in there as well, because a phase change will make a difference in the amount of enthalpy. 2 waters that are liquid. And we're going to calcium hydroxide. 2. Ooh, aqueous. No mistake. Plus C2H2 gas. So you take calcium carbide, add water, and you get calcium hydroxide and acetylene. Right? If you're an old-timey miner, you know what that is, because this is the reaction that takes place in their little headlamps. Okay, but we want to find out what is the enthalpy at 25 degrees. Okay, so there are equations that we can use. Well, if we start with the first one, let's see, is it going to help us? Graphite, calcium. Yeah, there's the carbide. Okay, it's on the wrong side. So we need to flip it, don't we? There's only one here and there's only one there. So all we need to do is reverse the equation and change the sign on the enthalpy. So let's see if we can keep them consistent with the arrows. We're going to put the calcium carbide on this side and make calcium and graphite a product. And the delta H here would be 62.8. And this is, these are all kilojoules. Okay. So that takes care of that one. How about the next one? Calcium solid, calcium oxide. That one we could use, since there's no calcium up here, we could get rid of that calcium there. Right, if we write it just as is. Right, put the arrow here and put the calcium and oxygen on this side. 1/2 O2. Calcium solid on this side, and then calcium oxide over here. Solid. Then that would get rid of this calcium that we don't need up here. And we keep the value as is. We didn't flip it. We didn't multiply it by a factor. So that one's good. How about the next one? Calcium oxide, water, and calcium hydroxide. We can get rid of calcium hydroxide if we flip that equation, put calcium hydroxide on this side. Yeah. So let's put calcium hydroxide over here. Aqueous. Is that one aqueous? Yeah. And then calcium oxide and water on this side. Calcium oxide and water. Yep. And we need to change the sign. Plus 653. 6.3.1. This one's a plus. Okay, so what does that do for us? Well, it gets rid of, oh, you guys let me get away with that.
I was about to say something.
Keep it negative. Put it where it's supposed to be, right? Calcium oxide on this side. It should have been a clue that I was adding up another calcium oxide over here. How was I going to get rid of it? There we go. Now we got this one. Got that one here. We got this one here. All right. Acetylene. That's the next one. Okay, that acetylene does need to go on that side. So I'm going to flip the acetylene. 2 CO2 and 1 water. And the products would be acetylene and 5 halves oxygen. Okay, and this will be plus 1300. Okay, that gives us acetylene here and here.
Attention, an emergency has been reported in this building. Please cease operation.
Fire alarm.
The building.
I should have remembered that they told us in the parent could be one, so we have to. Oh, it's warm outside. We got to go over to the big rock.
Attention, attention. Has been reported in this
We're already over time. But if you got to go, that's fine, and I'll just finish up later. All right, I'm gonna grab my paper.
I was gonna say, yeah.
Grab your stuff.
I'm good, I go to the big rock.
Yeah, we have to make it official.
Okay.
building utilizing the nearest exit, fire exit stairway. Do not use elevators. Do not use elevators. Attention, an emergency has been reported in this
There's those
building.
people now, we have first
Please
phase.
operate and leave the building utilizing the nearest exit, fire exit stairway. Do not use elevators. Do not use elevators. Attention, attention, an emergency has been reported in this building. Attention, attention, an emergency has been reported in this building. Attention, attention, an emergency has been
So is everybody good with staying a while? Because it's past the normal time. Yeah, 1:45. I was running over. We only got two more? Okay, well, let's finish this one up then. Let's see. Oh, which one is which? Is this it? Maybe. We'll soon find out. Okay. Let's see. Got that one covered, got this one covered, got that one covered. All right, and we've already canceled this one and that one. Let's see. This gives us two waters. No waters on that side, so let's look. We got one more to go. Oh, no, waters. We're supposed to have two waters. That's not good. I think it's this one. Yeah, this one. Okay. Calcium oxide. Right here. Get rid of that one. Carbon dioxide. Carbon dioxide. We haven't done that one yet. Okay, so the last one is graphite. Right. Plus O2 yields CO2. And we didn't change anything, so that value is minus 393.51. Okay, so this graphite goes out. Oops. No, it doesn't, does it? Because we need two of them. All right, so we got to multiply that one times two. What's 2 times 390 and 551? Do that in your head. 393.51 times 2 minus 787.02. There we go. That means we got two here, two here, two there. Okay, so now we can get rid of the two graphites. Two oxygens. Well, we got a half an oxygen over here and two over here. What is two in halves? 4 halves, isn't it? 4 halves and 1 half is 5 halves. So that one goes, this one goes, and that one goes. And 2 carbon dioxide, one here, one here. So we got anything left? We need that one, that one, that one, that one, that one, and the rest are crossed out. I think we're good. We just need to sum these up. All right, I already got 787.02. I just need to change this somehow. Here we go. 1,300 plus 653.1 minus 635.5 minus 62.8 plus. So I get minus 712.82. Okay. Go down here. Wait a minute. Oh, was that a fill? That was a fill in the blank, wasn't it? Why is it hung up? Come on. There it is. 712.82. That's why I put that there. Kilojoules. Is that endothermic or exothermic? No idea. Exothermic. So that miner's lamp is not just going to get hot from burning the acetylene, it's going to get hot from the reaction too. Maybe that's why they made them out of metal. All right. Okay. Let's move this one out of the way. All right. 60. All right, we've got electronic structure in this row. We got hybridization. This row, bond angles. Bond angles in this one. Okay, so we got molecule A, B, and C. There we go. And we're given this one to start with, SP3. All right, we'll get my different color out. Okay, what are we told? A has hybridization sp3 on the central atom. Molecule B has two more effective pairs. If it's got two more effective pairs than this one, where are you going to put them? We've used up the one S and all three P's. Yeah. Go to D's. D2, sp3. Molecule C is a diatomic and consists of a sigma and a 2 pi's. So sigma and 2 pi's means what? Remember, when you got a bond, right, it always has to be sigma before you can get any pi's. If you're going to have 2 pi's, triple's the only way to go. So that's sp hybridization. Okay, so electronic structure, right? sp3, tetrahedral. We just did one of these. 5, trigonal, and bipyramid. And sp is linear. Okay. Now bond angles. Here's the problem. That's electronic structure. We don't know the molecular structure. Question?
Wouldn't B be off?
Yes, you're right. You're absolutely right. 2, 3, 4, 5, 6. I better contact Dylan. He was asking me these when we were out there. Yeah, exactly right. It's octahedral. 2, 3, 6. Now, if we assume that all the positions are occupied by atoms, then the bond angle would be 109.5 degrees. That's the only possibility. How about this one? Well, let's see. If we got a square here, and then we've got something up here and something down there, then we can have 90 degrees here, right? We could have here to here would be 90 degrees, and then here to here would be 180. So 90 degrees and 180 are the possibilities, unless one of these positions is not occupied by an atom. So that, the only way to answer that one is just suppose that all of them are occupied by atoms. And then you could have 90 degrees and 180 degrees. Linear, there's only one possibility. 180 degrees. So you got one more? Is that it?